Hello, my name is William Wu, and I am a junior from Rancho Cucamonga High School, and this is my science fair project on statistical inferences on non-stationary increments self-similar processes via Lamperti transformations. So a general overview of this project is that I introduced a novel method to estimate the self-similarity index and the scaling parameter of any self-similar process via Lamperti transformations, and using this, I'm able to apply it to different processes such as the fractional Brownian motion, subfractional Brownian motion, etc. And this will be able to fill in gaps in literature, and I also provide code on GitHub for how to actually run this method. So for some background here, a self-similar process is a random stochastic process that exhibits the property where part of it resembles the whole. And in this case, it's characterized intensely by the self-similarity index, where a high index represents a smoother process and a low index represents a more rough path, as you can see from the images here. So the research objective in this case is to be able to estimate the self-similarity index and scaling parameters for all self-similar stochastic processes. And I just want to highlight that in literature right now, there does not exist such a generalized method. So the research I'm going to present here is going to be completely novel. And in this case, the research I'm doing this year is partly inspired from the research I did last year, which is to simulate all general stochastic self-similar processes. And this year, I'm going to be the lead author with a little bit of help from my research mentor, Dr. Peng. And I'm basically applying some of the methods and knowledge I learned last year with modifications on a project this year. So a key framework I'm using is the modified Lamperti transformation. And what's important about the Lamperti transformations is that it's able to transform self-similar processes into stationary processes and vice versa. And stationary processes have the property where the distribution is invariant under time. And this is going to be very important because it's much easier to work with than self-similar processes. So going on, I have two different algorithms to estimate the self-similarity index. So one is where sigma squared or the scaling parameter is unknown, and one where sigma squared is known. So for the first algorithm, I'm able to transform the process, the self-similar process, into a stationary process via the Lamperti transformation. And then because the second order moment of a stationary process approaches sigma squared, I'm then able to estimate h numerically using some version of Newton's method. And for algorithm 2, because we don't know what sigma squared is, the approach I took was to have the fourth order moment and then divide it by the second order moment to actually cancel out the sigma squared. And doing this, we're able to actually empirically estimate h again using the equation given in step 2. And going a little bit further than that, we're also able to estimate the scaling parameter sigma squared using some form of the same method. And this is all given by the Cauchy-Schwarz inequality. As a bit of application, I want to show how we could use our algorithms on a process, which in this case is bifractional Brownian motion. So bifractional Brownian motion is very popular. It's able to model a lot of results. And in this case, I need to calculate the autocovariance of the inverse Lamperti transformation of bifractional Brownian motion in order to actually use it. And then we calculate variance 1, which is going to be sigma squared. And a key thing to note is that for different processes, variance 1 is going to be different. For example, subfractional Brownian motion has variance 1 is equal to sigma squared times 2 minus 2 to the power 2h minus 1. So this just goes to show that for different processes, you need to do a little bit of extra work in order to actually apply the algorithm. So here's the proof of the theory. It's going to be a little technical, but key thing to note is that we use the estimation v of floor of n to the power j over n divided by n. So by taking the floor, we're able to only use the discrete observed samples and not the actual real process. So we basically prove here that the error converges to 0, which is basically bounded by Cn to the power of negative 2 beta. And this is going to converge to 0 as n approaches infinity. So basically these have the same distribution, meaning that the algorithms are going to be statistically accurate. So here are the results for the simulation algorithm or the estimation algorithm. In this case, I'll be able to simulate 200 processes of each type with path length 1024, and then we calculate the mean self-similarity index and the mean squared error. So notice that the mean squared error is going to be very low, meaning that it's going to be very accurate and that the results are going to be very competitive. And the estimation results for algorithm 2 are also given. Key thing to note here is that the mean square error is a little bit higher, meaning that it's a little less accurate. But still, as n approaches infinity, this is going to converge to 0, just that it's going to be a little less accurate because we lose some information since we don't know what the scaling parameter is. And moving on, we see that the estimation for sigma squared given by the histograms for two types of processes are also very accurate. They're nearly centered on the real value, and compared to some results from another paper given by reference 2, which I'll show later, it looks almost the exact same. So moving on to real-world applications, bifractional Brownian motion can actually be used to model the SP500, which is given in many results in literature. So running the estimation of the self-similarity index on the log returns of the SP500, assuming a bifractional Brownian motion model, gives us that h is approximately 0.586. And what this tells us is that the estimation algorithm is going to be very accurate because in the real life, people have done this for fractional Brownian motion, a different model, and also got around the same h. So this kind of opens up the possibility of using more advanced processes to model financial instruments and other types of real-world applications for more accurate results. And moving on to the conclusion. So what I've done is I'll develop a novel way to estimate the self-similarity parameter for similar stochastic processes and the scaling parameter for them. And this new method is able to work on non-stationary increments and self-similar stochastic processes, which has never been done in literature. So I apply these estimation algorithm to many different types of processes and also have the code available on GitHub where the results show low error and competitive results. And of course, I'm also able to apply it to real-world data. But the limitations do include that the self-similar process must be ergodic and has finite moments. So in the future, this work can be generalized to higher dimensional processes or locally asymptotically self-similar processes where they have non-constant h values. And here are the references and supplemental information. Thank you for watching and have a great day.